Alright, well, hey everybody out there. This is Obi-Wan Pez, signing on for N Simplex Pachinko. Um, so this is going to be my second stream overall, but this is going to be kind of the primary reason I started this channel in the first place, was to get some of the math stuff out there and be a more educational type channel. We'll see how it goes. There might not be a lot of demand for this, but you know, it'll be fun. So, so this week I am planning on doing a segment on Fermat's last theorem and specifically Beal's conjecture, which is a more modern take on Fermat's last theorem, and it will. I'm also intending on looking at a little bit of what I did to try to push it forward. Just playing around with stuff anyway. So, you know, not saying that I'm gonna like get the prize or anything like that. That's not gonna happen. But at the very least, just looking at Beal's conjecture, what it is, and some interesting things that I just tried here and there to push forward on it. So, let's start over here. Just as a reminder, yeah, I do have also the gaming stream, which is going to be either Friday or Saturday nights. Currently, I'm working on Outer Wilds, and if anybody hasn't played that game and is interested in doing so, you can watch my first stream with, you know, minor spoilers. It'd actually be better if you went and just explored on your own and didn't rely on me for anything, but you know, it's an interesting time. All right, so real quick. So Fermat's last theorem is an interesting little idea that was put forth by Joseph de Fermat, who was a French, actually businessman, but he became a mathematician through practice. So he spent a lot of time reading and spent a lot of time looking up all sorts of cool stuff within mathematics, and was reading a book called Arithmetica. Oops. By the Greek mathematician Diophantus. And the idea that he came across was a one of the what are called Diophantine equations. And so Diophantine equations have sort of a similar structure to them. Now they can be all sorts of different structures. They can have fractions, or some of them are similar to this, like 1 over x to the n plus 1 over y to the n plus 1 over z to the n. It can be all sorts of stuff. But the idea was Diophantus came up with a bunch of different equations that look sort of similar to this. The one that Fermat really zoomed in on was x to the n plus y to the n equals z to the n. And he claimed, in the tiny little margin of the book that he was reading, that he had a proof for no integer solutions, for n being greater than 2. And x, y, and z all could not be 0. So those are the only restrictions that he actually gave. He then went on to say that he had a marvelous proof of this theorem, but it would not fit in the margin of his book. And for decades, really, that little note sat in his book, and nobody ever looked at it until Fermat died, and his son ended up taking all of his stuff out of his house, looking through his books, and finding this particular statement, that he had a proof for this particular equation with no integer solutions, n greater than 2, x, y, and z can't be 0, but it wouldn't fit in the margin of the book. His son tried then, being a decent mathematician himself, tried to also replicate his father's work to try and see if he could do it, and he couldn't. And then he went to the local university and asked them, and the mathematician said, "Oh, that's very interesting. Nobody's come up with an answer for that in centuries, so let's try it." And they tried exactly what Fermat could have tried, and again, they just couldn't find any actual proof of this. So it seemed like Fermat might either, one, have actually come up with a proof, but possibly it was wrong, or he figured out there was something wrong with it, or whatever. And the pages that he then actually translated this proof onto, he just threw in the fire, threw away in the garbage, what have you. Or possibly, two, he didn't really have a proof, he was just messing with people. As much as I like that idea, I think the first option is probably a little more likely, that he did in fact think that he had a solution, but it just didn't end up panning out the way he thought it did. So... Oops. Sorry, I had my note here for... Oh, don't you love it? It's one of the problems with being a mathematician. You got so many papers around the house. All right. Yep, here we go. Don't get me wrong, I can do most of this from memory, but, you know, I do like to have my actual notes next to me so that I'm not making stuff up. I did hear most of my students probably just laugh then, so that was interesting. All right. Alright, well, never mind. I'll remember most of it anyway. So, Fermat's proof of this was lost to history, and nobody actually was able to replicate that he had a proof, so a lot of people have decided that the proof that he had was, again, either wrong or there wasn't one. And it wasn't until actually 1987, 88, when Star Trek The Next Generation came out, they had an episode called The Royale, wherein Captain Picard is kind of working on a data pad trying to figure out something, and Riker asks him what he's doing, and he says, "Well, I've just like to kick around this idea. People have never solved this. It's a, ancient history or ancient mystery that we don't understand." Joseph, oh boy. This is the other problem with Pierre. Okay. So Pierre de Fermat, I said Joseph earlier, sorry. Pierre de Fermat was a French lawyer in Parliament of Toulouse, France. And again, he did a bunch of mathematics type stuff just for fun. So Pierre de Fermat came up with this, and again, Captain Picard in Star Trek The Next Generation says that people have been working on this for centuries and haven't been able to figure out what his thing is. So he likes to kick it around every now and then and see if he can make any, headway on it. And throughout the rest of the episode, there is basically a plot. The A plot is that Riker and the others are stuck within this weird hotel. Anyway, you should watch it. But the idea here was that, again, Fermat's last theorem lasted for hundreds of years until, again, nobody was able to solve it up until the 24th century when Captain Picard is working on it. However, it turned out that a man named Andrew Wiles, who was, again, gotta look for my notes here. So Andrew Wiles was able to solve Fermat's last theorem, and I believe prove, in 1993. He then found some holes that were in the theorem, and this was based on the Taniyama-Shimura conjecture. I don't really have all that much information about what all these little individual conjectures were all about, so I'm going to keep moving on here. And in 1994 and 1995, Wiles and co-authors ended up printing updated versions of Fermat's last theorem proofs, which all ended up working. Wiles' proof eventually succeeds by using elliptic curves, not using elliptic curves, and using Galois representations, using a lot of items that were proven within the centuries between Fermat and Wiles. So a lot of people, mathematicians, are of the opinion that Fermat could not possibly have proved, he certainly could not have proved it that way. That his proof would not have used the same stuff as Wiles' proof. And that there are some Fermat fanboys, if you will, who said, oh no, it's absolutely possible he could have solved it, but just not using that method. He was such a brilliant guy, he would have come up with his own sort of thing, and we just haven't been brilliant enough to discover it. Whereas that is potentially true, I don't believe a word of it. I think that, again, as I said before, Fermat either thought he had a proof and then it failed, or he was just trolling people. Again, leaning toward the first one. Hey, Soul Reaver. Alright, so just discussing a bit about Fermat's last theorem here, and the so this was again 1993 through 95. Ended up being solved by a guy named Andrew Wiles. Using very modern, by comparison, mathematics compared to what Fermat had at his disposal. Okay, so the Beal conjecture goes on to say, alright, given x, y, and z, and a, b, B, and C are all members of the positive integers, at least for simplicity. There we go. I gotta make sure I get the wording right, because so it is actually a generalization. So it says that any of these numbers are positive integers, and x, y, and z are all individually greater than 2. If a to the x plus b to the y equals c to the z, then a, b, and c have a common factor. All right, so what I'm going to do is, because I have a user requested question, I'm going to let you mull this over for a little bit, and then I'm going to talk about how I, like I said, tried to push this a little bit forward. I didn't really make any like huge strides or anything like that. I doubt it. So I'm going to come back to this, start a new whiteboard, and talk about the question that Soul Reaver has. So now make sure I get this right. So we got given. This is calculus, by the way. So if anybody is watching this from the future, this is Calc 1. Given that y equals x squared minus 5x plus 6. So, given the graph of y equals x squared plus 5x plus 6, find the intersection points, points, to any tangent line through the point 2, -1. So a little bit reworded from the way that you had done it. If anybody is interested, you might want to go follow Soul Reaver. He is a student of calculus and also a tutor for, I'm calling you out here, so, and tutor for any of the earlier maths. So if anybody has any questions, also I believe you said you do a little bit of physics and engineering, right? I'll let the stream catch up. Yep, physics up through Kepler's laws. Okay, cool. Nice. Okay. So, roughly, again, this is the question that was asked. So my personal start for this is, well, I reworded the question, so that might be a first. If you have a question and you're not quite sure how to approach it, this is usually a good thing. Just try and see if you can pull it apart and see if like rewording it in a different way kind of helps you understand it. It's just one thing that I do, like when I'm doing higher level stuff, usually like differential equations, multivariate calculus, and linear algebra are the highest ones that I can teach at my institution. I should probably mention that. So, this was supposed to be part of the introduction part at the beginning. I am a math teacher. I have been teaching at, well, a community college in the Mid-Atlantic region for about 10 to 15 years, so somewhere in that region. Um, I've taught everything from basic math all the way up through differential equations. I have not yet actually taught multivariate calculus and linear algebra, although I am kind of thinking about doing it sometime soon. Um, you know, pandemic, right? It's the great time to learn stuff. Okay, so as I'm standing up in front of my students, I will usually say, like, okay, let's reword the question, see if there's a better way to phrase it in terms that you like. So, like, these are the terms that I use. Maybe you don't like the way I say it. That's perfectly fine. Try to make it yours. All right, so once you do that, sorry, I am a little obsessive sometimes. Once you do that, then you want to look at this. And second thing that I try to do is draw a picture. So I know that this equation here is going to be a parabola. It's going to have, since a is equal to 1, it's going to be opening upward, and it's going to have the same standard parabolic pattern that all parabolas have. So it's the same shape as the parent function y equals x squared. It's just going to be in a weird location. If you want, one of the things that you should probably do when you're trying to draw a picture is to factor this thing and try to find the zeros for it. So if we're just doing this kind of in our head really fast, you don't actually need this for this particular question. I will say that, right? You don't have to do any of this stuff, but it is kind of a good idea if you're just trying to understand the question better as a whole. So what I do here is I'm saying, okay, I want the zeros for x squared minus 5x, all right, minus 5x plus 6. All right, the way that I do this in my head, again, this is more geared toward like algebra students, but you never know. If you don't know this one, it's a good thing to do. Rather than doing the whole like multiply to this, add to this, let me figure out what it's going to be, what I will personally do is I will say, let's come in here and find the values for A, which in this case is 1, times C, 6, which gets us 6. All of the different possible factors that we can get for this are going to be based on this number. So 1 and 6, 2 and 3. All right, we know this. This is basic Algebra 1 stuff, right? But, and I still do this to my calc students and my differential equation students, even though it's like basic algebra. I will still come back to this because it's always better to come at this from a different way and have a new perspective. And as I said, if anyone out there has other perspectives on things, please share them with me because like I want to learn that too. All right, the product was positive, which means that the signs between these two things have to be the same. So the signs are going to be the same, and this is what happens when we add those two numbers together. We get this negative 5. Well, how do you get a negative number if you're adding two numbers? The bigger number has to be the one that they give you the sign for. So here, this has to be the bigger number, so the bigger number will be negative. And then some of my students immediately jump to, well, if this is negative, then it's going to be a negative 6 and a positive 1. Done. And again, there's a problem with that. Here, we already said the signs have to be the same. So the positive 6 at the end, or the positive 6 product, means that the smaller numbers also have to be negative. So now which ones add up to negative 5? Well, there's only one. Excuse me for 1 second. I do have... one of my colleagues is trying to get a hold of me here. Okay, sorry. So, urgent question about tomorrow's meeting. Okay, so anyway, This -2 and -3 are what happens when you add, when you split this middle term out into two pieces. Now, I did not actually learn this particular method of factoring until I started teaching, so this is one of the reasons why I keep teaching it, even if like students now are taught it, which a lot of them are. All right, so this is going to be an x squared, this is going to be a -2x and a -3x and a +6. I will then work on this through group factoring. So group the first two, group the second two. Out of the first two, you're going to take an x, and you're left with x minus 2. Out of the second two, this negative here would be really convenient if you could take it out. And the common factor between them is 3. Why did I say it was going to be convenient? Well, -3 from -3x is going to be just x. -3 out of +6 is -2. And now if you look at the terms, we have multiplication by the same term, so we can factor that out as well. So this is going to be x minus 2 is factored out. Literally, x minus 3 is left over. So this means that we have zeros at 2, 0, 3, 0. Now, this is kind of obvious with a equals 1 being the way that we had it here. However, if a was any other number, let's say it was like 3, I often do this sometimes with like doing a 3 up front and a 2 at the end instead of a 6 at the end, just to see how it goes. This is mathematically sound, so I like this method. Sometimes some people like dividing, like you bring your a value from this side all the way to the end. I don't really like that one because it's not actually mathematically sound as it sits, but you know, technically the trick works. I just don't like it. Anyway, enough rambling. Okay, so 1, 2, 3 going across. We have zeros at 2, 0, and 3, 0. If we want to know where the vertex is for this thing, again, this is kind of optional. Remember that B, whoa, boo. There we go. Nope, that is x. The x for the vertex is going to be equal to a -b over 2a. Sorry, my mouse froze there for a second. I hate it when that happens. In this particular case, b is -5, so -5 over 2 times 1 is a +5 divided by 2 for the x for the vertex. And then the y for the vertex, we're just going to plug in 5/2 squared, not running off the page, good, minus 5 times 5/2 plus 6. This is going to be a 25/4 minus 25/2, and like I said, I know this is getting a little pedantic maybe, but 25/4 is half of 25/2, so that's going to be a -25/4 left over, plus 6. 6 is 24/4 plus a -25/4. So y for the vertex is going to be a -1/4. So we come over here, and if we do something like, you know, let's just call that 1 arbitrarily, 1/2, the vertex will be here. Okay, and then we come up and out this way, and up and so close. Up and out that way. These will continue again, steeper and steeper as we keep going up. The initial question said we have a point at 2, -1, and we want the, come on, mouse froze again. There we go. We want the tangent lines that went through this point. So first off, one of the tangent points is going to be that way. Let's see if I can actually, I want to see if I can do this with a ruler. not what I meant. All right. Okay. So we go like this. Let me say that this is going to be okay. Just lagging behind, it's fine. Alright, so we're going to get a tangent line that looks like this. And we know we're also going to get a tangent line that looks, roughly speaking, I don't have it exactly in the right spot, but it's fine. Roughly speaking, tangent line that looks like that. Hey, more circle. So the whiteboard itself is literally just Microsoft Whiteboard. It is free to download. I like free. Free to download from the App Store on Microsoft, and it has all this functionality. It does have its own little quirks and problems that you can come up with, but I like it. It's, you know, for what it does, it is better than another whiteboard for a free provided whiteboard for a company that also provides connection software to your classes. Wink, wink, nudge, nudge. So I also like this in that I can bring in pictures and stuff like that if I wanted to. So down at the bottom I have a couple of tools. I left them off the page actually, but let me just pop it up here real quick. So at the bottom I have these tools here. So it gives me all my pens. It gives me multicolored ones too. So rainbow and galaxy. Neon highlighter, eraser, ruler, lasso select, which allows you to just grab around stuff. You do have to use your pen for that. I keep trying all the time to use my mouse with it, and it just moves the page. So don't do that. So you have to use the pen and like circle something, and then once you do that, it selects just the stuff that you lassoed, which is very nice, because then you can just grab that. So if I want to grab one of these blocks of blocks of text, and I don't want to grab this other stuff that's here. If I just wanted, that's interesting. Okay, cool. If I just wanted to grab this and not the zeros down below, I could lasso all this stuff and then drag it out here. Maybe not. No. Okay, I don't know what went wrong there. I think it might partially be due to lag. Okay, let's try it again. So I'm gonna like very carefully grab all this stuff. Now it's actually selected it, and you can see the stuff come up there. Now if I drag it over here, it should come this time. Okay, well, I only grabbed one of them, so maybe if I grab the box, but anyway, you could do all that. It's pretty cool. Much less sophisticated than CAD. And as far as a writing tablet, this is a bamboo, Wacom bamboo tablet. This is like the really cheap one that my boss actually gave me years and years and years ago and was like, figure out if you can do something with this. And then like she's not my boss anymore, so whatever. I didn't touch it until the pandemic, and I'm like, ah, crap. Maybe I ought to do something with this. So yeah, she's not my boss. It's fine. So anyway, okay. So what I would suggest is, draw in just as a picture, draw in the two tangents that we see here that should exist. So you know at this point there's only going to be two that are going to go through this point and be tangent to the actual lines up here, or the curve, the parabola. So then the point was, well, now we have to figure out what the equations for these lines are, and or, well, we have to figure out what the intersection points are. Again, I kind of like, let's find the lines for these things, but it doesn't much matter. You can do either one. So, yeah, no problem. If you want to figure it out on your own, you can, you can head out. Now, okay, so this one up here, and in fact, we're doing this in general, so it doesn't much matter, like either one. We're going to say, okay, the lines that we have that are going to be tangent to the parabola have to be tangent at those particular points, which we're going to call, like, you know, a point up here and a point somewhere here. Wink, wink, nudge, nudge. We totally don't know what that is. When you're drawing pictures, you don't want to necessarily, like, be suggestive of any particular answer. You just want to make sure that your audience understands that, like, I don't know what this is, technically. We going? Come on. Come on. Yeah, never trust the drawings. No matter how much it looks like it's supposed to be that way. Never trust the drawings. All right. So we know that these 2 points are going to be connection points for our tangents, and that does mean that I've gotten out of practice in the last month. I always did that, going away on summer vacation when I was in, you know, elementary school, and then you come back and your handwriting's atrocious for like a month. Yeah, so the tangent lines must share the slope with the parabola at intersection points. So because the tangent lines have to share the slope with the parabola, using calculus, you can say, okay, the slope of the parabola is going to be y prime, which you had already figured this out. So good job, Soul Reaver. Right, taking the derivative of x squared minus 5x plus 6. I'm just going to do the long way here. So d dx of x squared minus 5x plus 6. Just make sure everybody gets it, just in case. All right, so y prime is going to be 2x plus 5, or minus, sorry, 2x minus 5. So the lines and this particular parabola have to share that slope at those intersection points. Okay. So then where are these individual points? Well, technically we don't know. So, like, we just label them. So this one here we'll label as A. Mouse froze again. Hang on. There we go. A comma F at A. And this one we'll call B comma F at B. Because this was totally f of x up here. We'll just pretend it's fine. Okay, so we got this. Now, if we want the equations of these lines, we can say, okay, well, the equations of the lines, we could do point slope formula. about as good as any, I guess. Um, sure, why not? So the example in the book there got you that f of x was going to be equal to x squared minus 5x plus 6, which then had to be the same as, sorry, let's say it just had to be the same as 2x minus 5. Just want to make sure. Because we could go about it a long way, but at the same time, we don't necessarily have to. I gotta watch my head there. Okay. So if we wanted to find, for instance, a comma f at a here, we could say that this is going to be a plugging in. Yeah, just what, or the way that the book solved it. Was it that they took f of x and then set it equal to 2x minus 5? Just set those two equal to each other. So like f at a was equal to this. That's just algebra, but... Okay, so we can label this like L sub A and L sub B. Oh, they did general. Yeah. Okay. So I'm using A and B for different stuff. Might as well just go our own little way here. All right. So L sub A is going to have the equation. Let's see. I'm going to do point slope for this. So L sub A as point slope is going to be y minus y1 equals m times x minus x1. Okay, and we know that this point here was 2, negative 1. So we're going to go with, all right, our y value is now going to be f at a. We'll leave this one as our general. So f at a minus our y1 is now going to be, the y value of the known point, so negative 1. So this is going to be a little bit different from what they did, but it'll be okay. Our m is going to be, let me just say, I really hope that this does actually work, because sometimes I've just been like throwing stuff out there for my students and then been like, oh, it says a equals a. Great. That doesn't help. All right, m is then going to be our slope function, so 2x minus 5, but our x value is now a. So parentheses 2a minus 5 is the slope. We don't know what a is, but that's cool. That's fine. Times x, again, the general one is a. And then, you know what, yeah, this is going to be fine, but x1 is now 2. This is going to get you the equation that they had in the book. Maybe. Yes, should. All right, f at a here is now going to get plugged in down here. So a squared minus 5a plus 6 plus 1 is equal to, now multiply all this stuff out, so 2a squared. Like I said, this is a little bit like a long way, but it works. Here we have a 2a times a negative 2 is going to be a negative 4a. Negative 5 times a is negative 5a. And negative 5 times negative 2 is positive 10. And move everything over just because I like keeping a squared positive. So here we're going to have a squared. Yeah, I'm right at the bottom. Okay. This is going to be a plus 5a with a negative 5a, so those are gone. Why, thank you, more. Took me a minute to realize who you were. I was like, wait, I know that name. All right, anyway. All right, happy pirating. So add 5a to both sides. This is now going to be gone, so that one's out, and we just have the negative 4a that was here. And then we have a plus 10. This is a plus 7. Subtract it, so 10 minus 7 is going to be a positive 3. Yeah, cool. All right. That's the one you told me about earlier. There we go. So we take this. 0 is equal to a squared minus 4a plus 3. And again, do the same thing with, do the same thing with the factoring. This ends up being a minus 3, a minus 1. And so a equals either 1 or 3. And then f at a is going to be whatever those values end up being. So plug in a 1, we got 1 squared is 7 minus 5. 7 minus 5 is 2. Or 3 is going to then make 9, 15, and negative 15. Yep. 2 in those order, and these are coupled, so you cannot like trade order of the sets and stuff like that. Now again, I did this generally, and we didn't even need B. We just needed A to be a general variable for it. But yeah, cool stuff. I love calculus so much. It's I keep telling my students, and a couple of my pre-calc students this semester were like chatting with me more recently, and I told them, you know, calculus is like this reset where if you go into calc having fairly strong algebra, it's just really like the difficulty level almost goes down to nil, and then you just have to start building back up again, as long as you know your algebra. Of course, that's sometimes the problem. Yeah, anytime. I'll be here Wednesdays. So yeah, I mean, I had Stuart back in high school, the one that had like the sliced torus on it that looked like a donut that had been like carved out in places. And we were using a different one. Yeah, it's really odd. I mean, it's not odd. It's not surprising technically that a lot of the like good calculus books are kind of not used anymore. The publishers push a lot of stuff, and you know, not to really hate on the publishers. They do have to make money and stuff, and they are getting good books out there in the public, but at the same time, so many of the textbooks these days are kind of like, let's rehash everything and then let's put in flashy graphics. And yeah, but why? You don't need flashy graphics necessarily if you're explaining stuff well. Which is amusing because so many of our institutions now are pushing for zero textbook cost, so ZTC courses. And so many of us have decided that we're going to start using, we're just going to start using, bloody hell, sorry, blanking. We're going to start using stuff on like OpenStax. And so you go to OpenStax and there's a free textbook which doesn't have like any graphics in it, or very few. It's all done in LaTeX. And so it's like, you know, if you try to read it, it's good, but at the same time it's just kind of like everything is monotonous, and it's just like Now some of the other stuff is kind of like that too. I don't think I have my tensor calc book here, but no. Anyway, when you get to linear algebra, if you ever decide to go for it, it's fun. I have... there's a teacher... Yeah. OpenStax is kind of like... I think the problem is that it's such a new resource that a lot of people don't know, like, aren't using it to its full capability. You know, they basically just chuck a textbook up there because they wrote one. And although it's good, technically, it doesn't necessarily catch your eye, and it's not necessarily written in the best way. Like, it's written well for mathematicians. It's just not necessarily written well for students. Do you mean this long S? Yeah. So, yeah, integration is another really important and, pardon the pun, fundamental piece of calculus, and it is amazing once you actually get to that, because it's just like, okay, like how did this not? How is this? Ooh, hang on. I just messed that up. Okay, whatever. Cool. Yeah, the integration stuff is really interesting once you get to it. I mean, I'll give you a hint if you want it. Whoa. All right. So what this really means is just antiderivative of f of x. So all it means is if you took the derivative of some function, this is what you get, the thing in the argument of the integral. And then what do you do from there? Well, you work it backwards and you say, okay, let's base this thing off of one of our like most basic functions that we can get. So if you see something like, let's do an easy, I'm just going to do an easy one for you. So this will be super simple. Right? What's the antiderivative of 2x dx? So this is saying, what function do I need to take the derivative of to get 2x? Well, okay, that's, yeah, pretty obvious what that one is. This is going to be x squared. But then the question is, which x squared? Because I could have had x squared plus 1, or plus 2, or plus 3, or plus 4, right? Or minus 1, or minus 2, and I don't know what it is. It could have been any constant. That is perfectly allowed. You could have any constant here. You could have any constant here. So what we do is we say there is an arbitrary constant plus c on the end of all antiderivatives. Now for antiderivatives, this becomes really easy, right? You can just start working with stuff like this and say, okay, what is the integral of natural log of absolute value of x dx? Right, so this gets a little bit harder, but it's not actually any harder really. Oh wait, I think I went backwards. Yes, I totally did. Sorry, natural log is extremely hard. know it. I teach this, I promise. Um, so what's the antiderivative of 1 over x dx? There we go. All right, so I gave it away. That is the natural log. And it's not just the natural log of x because the domain over here was not restricted. So it was all real numbers except for 0. This has to be all real numbers except for 0 too. So that has to be the natural log of the absolute value of x plus c. And this is one of the things that calculus teachers will do is they'll say, like, if you ever forget the plus c, you're going to get a -1 automatically. Or like -0.5 on a 1-point question or something. It's a little draconian, but gets the point across. It's a little bit like making something that happened to me when I was a kid. You spelled a word wrong, write it 50 times. You don't get to go to recess until you're done. Did actually happen. All right, now the fun thing is what happens when you get something like taking the integral of, like, 10x dx. Newton, great name for it. Yes, I will definitely do one coming up next. And Violets, hi, welcome. Okay, so what we can do here is we can say, well, this one follows the exact same protocol as that one up there. It has the same form. It's not exactly the same, but it has the same form. So absolute, nope, that's not it. Taking the antiderivative, there we go, of 10x dx. We could say that this is the same thing as taking the antiderivative of 5 times 2x dx. And constant multiples for derivatives and now antiderivatives are just going to pass through because they're unaffected by constant multiples, right? So constant multiples are able to pass through integrals and derivatives and antiderivatives. So here the 5 can come out, and then we get 5 times the antiderivative of 2x dx, which then means this is going to be 5 times x squared plus c. Technically, you could say that this is 5 parentheses x squared plus c, but when you multiply c by 5, it's also c. It's another constant multiple. It's an arbitrary constant. It doesn't matter what it is. Now, the only thing that you do have to worry about is if there are multiple constants in a single problem, then you have to watch out and make sure you're not like changing the value of one and not the other, and renaming something just because it, oh, it's an arbitrary constant, so therefore this c will rename it to c. Well, no, you can't necessarily do that unless you rename all the c's in the exact same way. So we're getting far afield. It doesn't matter. All right. So what all of this comes to is what Newton is hitting at here, in that in these antiderivatives eventually, so eventually it's found out that taking the antiderivative within a certain area of a graph is actually equivalent to finding the area under the curve. So you get a function like this, you want to find out what the area under the curve is from A to B, and let's just call this f of x as usual. Then this is going to be the integral, this stuff here, the area of this particular non-box is going to be equal to the integral from A to B of f of x dx, which is then going to get us by the fundamental theorem of calculus, f at B minus f at A, big F and big F for both of these. All right, see you later, Soul Reaver. Yep, lurking. I got you. So capital F now being the uh, antiderivative function. So we'll call these. Oh, yeah, we didn't. So you're not technically supposed to do multivariate calc until Calc 3, but interesting. Okay, so anyway, oh, I put that right behind my head, of course. Boop. All right, there we go. So anyway, we're talking about areas under curves, right? So if you want to figure out the area between two curves, then we're talking like, all right, you've got f at x here and g of x here. So let's say you want the intersection point up until here, wherever that is. Lost my mouse. So we'll still call this B. Still call this one A. Yeah, well, that's what he's saying, is that it's 4 dimensions. It becomes a hyper-geometric figure. So hypersphere, hypercube, all that stuff. And technically, if you want to look up stuff that has to do with higher dimension, I cannot recommend this guy enough. Look up the game Miyagakure. No, it's not a dumb question. It doesn't make any sense because we're only in 3 dimensions. So look this guy up. He has Miyagakure. He has a website that he did a set of 4D animation tools. I'm just gonna like throw out all these other people that you should watch because I'm really excited about stuff. I don't remember what his handle is, but his name is actually on his website too. So if you look up Miyagakure, it also comes up with his blog, which has the 4D animation tools. So watch the video that's attached to it because it is amazing. Yeah, I really like Grant. He's a great guy. Anyway, so over here, if we're talking about finding the area between two curves, really what you're doing here is we're saying that we want the area. Let's draw an x-axis. We want the area under curve F, which is the blue one. This is going to not look very blue for very long. Is anyone colorblind, by the way? Just making sure. And also we're finding the area under the curve G to the x-axis. Now this can be brought back all the way to geometry, like geometry 1. How would you find the area of this thing? Yep. Alright, so you take the area of the square, you subtract the area of the circle, and then it'll get you the area of this little box with a hole in it. Right, I love doing symbolic stuff like this. It makes it easier to figure it out and easier to at least organize everything. And if you know how to do this, like the symbolic organization, you really understand the concept behind all the stuff. So, like when we were doing some of the earlier calculus stuff up there, if you get kind of an overhead view and you relabel, reword the problem, a lot of times it's the same as this. You're just kind of organizing everything in a way that makes sense to you. And then you can start working on the actual problems. Like if I didn't know how to find the area of a square, I mean, that's a problem. But if I didn't know how to find the area of a square because I'd never been told and nobody ever, whatever, I don't know. I could just symbolically write this out and say, okay, you solve the problem. You know how to find the area of a square. You do it. Now, I will say, right, it's not that simple. But if we're talking like, if we're talking much, much higher math, somebody needs to do some like higher order Fourier transform on some crazy function. And then that Fourier transform is going to get affected by another program in another way, right? Like I want to be able to, sorry, I want to be able to organize this in such a way that I can just kind of plug in the little module that I need in order to do something. So, oh, you want me to find the Fourier transform? Okay, we'll take this program that finds the Fourier transform of this particular function and then run it. That's it. If you do anything in programming, right, that's going to be pretty much the same. We're going to look at that and say, oh, well, yeah, I want to take this program that somebody wrote over here and I want to plug it into my program. And if you write it kind of in this way, you can say, oh, and I know exactly where it goes because I need it to be here. Anyway, so this is an analog here. This picture is really an analog of this. It's almost the exact same thing. What we're doing here is we're saying that F, the area under F, is the entire blue region. That's all of this stuff. But we only want the black region that's in between the two curves. So you get a saw and you chop off G, right? So we're cutting the function F and the area underneath it at the function G. So really what we want is the integral of f of x dx minus the integral at g of x dx. So the area under f minus the area under g. Now the good thing about integrals was that, just like derivatives, when you are adding or subtracting separate integrals or derivatives, they can be brought together provided they have the same terms. So these could be two completely different functions. That doesn't matter. What matters is, are they integrals of the same variable? So here we have integrals of f and g, but they're both on x. So when you have the integral here, this can now make integral of f minus g dx. So whichever way ends up being more convenient, you can do that as your notation. If you want an example, we could do f of x equals the square root of, let's do x minus 1 plus 2, just for fun. And g of x equals 1 over let's do a plus 1 out there, x plus 3. All right, these roughly look like functions that could very well be something like this, right? And let's say that b is going to be defined and a is not. So b is going to be equal to, you know what, we're going to say so we're going to do this on the interval. I'm going off the page. Okay. Let's move it again. This is fun. It's just going to be meandering the whole time. It's going to be awesome. Okay, so on the interval, x equals, x belongs to, start at some unknown a and end at 4. Technically, this is a to b here for both these. And if you're doing definite integrals like this, they do need to have the same limits of integration, so a to b. All right, so if we're going on the interval a to 4, we know that a is where they're going to intersect each other. So let's hope they intersect each other. Now that I'm looking at this, whoops. Well, we can find out. So where are they going to intersect? So this is where f equals g, square root x minus 1. This is not going to be nice either, is it? Equals 1 over x plus 3 plus 1. Oh yeah, that's going to be nice. It's going to be ugly. All right, cool. So I would suggest getting stuff kind of on one side-ish. We're going to subtract 2 here. Square root x minus 1 is equal to 1 over x plus 3 minus 1. Okay, this is now a, yep, we can multiply both sides by x plus 3 right on the edge. Okay. Okay, over here we get a division, and this divides out. So here x plus 3 divided by x plus 3 is going to be 1 minus 1 times x plus 3 is equal to, over here we just have this x plus 3 times the square root of x minus 1. All right, and then here, in order to get rid of the square root, we have to square everything. Sorry. All right, I'm actually going to keep terms separate for a little bit, because I don't think that this is going to be awful. It's going to be a little weird. Might be a little gross, but it's all right. We'll make it work. So this is going to be x plus 3 squared times x minus 1. All right, if all terms are squared, these are multiplied, so square each term. Is equal to parentheses 1 minus parentheses x plus 3 squared. Like I said, I'm being a little weird, but that's just me. Here, if we multiply this out, this is going to be x plus 3 squared times x minus x plus 3 squared is equal to 1 minus twice x plus 3 plus x plus 3 squared. Okay. Yeah, it's doable. It's not that ugly. So here we can actually combine like terms. And actually not that one, just that one. So here if we add this term here, yeah, it's all like terms, never mind. I'm okay, promise. All right, so this is going to end up being the same as that, and these two things added together are going to get us a 0. So that's gone. Whole term, just right out. So this is one of the benefits of also, if you don't like the way something is structured, You can also just change variables for a little bit. I could have up here, for instance, said let x plus 3 squared parentheses equal a. No, that's bad. Don't use a. I don't know. Capital A. Sure, why not? And then down here, this would have been like capital AX minus A equals 1 minus. Oh, that's not the same term. Nope. Nope, 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 nope. Catch me, because I will constantly do things like this. Those are not the same terms, right? These have squares on them. This does not have squares on it. So, oops. Yeah, I do stuff like this all the time in my actual class. Students get really mad. I'm like, no, look, this is stuff that you do too. I mean, okay, so that's going to be 2 x plus 3 squared. Okay. Oh well. It was fun while it lasted. Alright, we get a 1 there. That's going to be equal to, now this thing, x plus 3 squared times x. Hi, Freddy. Great name, by the way. And Silly Gnome and Extra More. Welcome. You know, it's the weirdest thing. Here I am doing math, and I got like 6 people here. I was doing some gaming stuff on Wednesday, and I had 0 people. It's great. No, I know. Many more people who actually do gaming. Anyway, so here, we got x plus 3 squared is going to get us x squared plus 6x plus 9 multiplied by x. 1 minus, multiply this through, is going to be 2x minus 6 plus, over here, this is going to be twice the same thing that we had on the other side. X squared plus 6x plus 9. So there is an argument to be made. Yeah, there is an argument to be made to doing this stuff as soon as you get it. But at the same time, like, I do like elegant kind of solutions where you just say, oh, well, I don't have to necessarily multiply everything out as soon as I get it. I can hang on to that for a little bit. Anyway, yeah. So this is, before I completely screwed up, this is kind of the point of algebra, is to be able to say, I'm going to take something that I don't really like the look of, and I'm going to replace it with a variable. And just say, like, okay, well, it's going to be a now instead of, you know, x plus 3 squared. And this is one of those things that, like, if you do a lot of math, you start recognizing a lot of patterns. And patterns are really the thing. So, if anybody is interested, I have... I unfortunately don't have a link to it or anything, but there was a good documentary done, God, 2004, 2005, I think it was, called The Story of Maths by Dr. Marcus de Sotoy of the BBC and Oxford. He did a trip around the world and did a whole lot of math history. And, like, you know, where did civilizations come up with ideas and stuff like that? And I absolutely love it. I actually, at my school, try to teach a bit of math history with a bunch of, you know, as I'm going through the content. And, you know, some students are a little weirded out by the fact that, like, a math teacher's doing history. But at the same time, a lot of them are like, oh, well, this makes a connection to something else that I actually like. Or they hate history and math, so that's just double whammy. But it gives a more, like, human connection to things, and being like, oh, it's not this it's not this abstract, math is not this abstract thing that I can't understand. It's actually like a human endeavor. People worked on this. It took thousands of years to get where we are. All right, so on this side here, I actually do have to talk occasionally. 1 minus 6 is going to be a negative 5. We get a minus 2x, and I am out of room. So, yeah. Are you doing that as part of your major? So it's going to be a plus 2x squared plus 12x plus 18. Okay, and x cubed is over on this side, so we'll move everything to the left. It's going to be x cubed. Yeah, the only people at my institution originally, where I went for my undergrad, the only people who had to take math history were math education majors. So only the people in that small, like, niche little world, it was a requirement. The people who were in the rest of the math department could have taken it as an elective. So if they just needed like some random extra math credits at the junior level, they could have taken that. I'd originally majored in physics. It was interesting. I was originally a physics major. I was so gung-ho about it. I was going to be an astrophysicist, just like Stephen Hawking. And this is even before I knew who Neil deGrasse Tyson was. Yeah. So I teach math at college level. I had originally planned to teach at the high school level, and I just couldn't deal with it. No offense to any high school students out there. I mean, it's not really, my students were not really the problem. It was the system and the system and parents. It's fine if they just ask, hey, everything okay? But end of the semester, I had a parent storm up and be like, you need to answer to why my child failed. I'm like, you didn't see the report card? You didn't see the 10 messages that I sent over the course of the semester? And she was like, what phone number did you send those messages to? What email did you send those messages to? And when I produced them, she goes, those are his. Okay, I'm going to let you two sort that out. I'm just going to step outside. So, all right, here we go. X cubed plus 4x squared. This might be a little over the top for what I was planning on doing, but it's okay. So this is now a negative 12x plus 2x is going to get us a negative 10x, plus 9x is going to be a negative 1x. Lovely. And a negative 18 plus 5 is a negative 13. Equals 0. All right, looking at this, I don't think we're going to get anything nice out of this. So, oh well. But I should have figured that wasn't going to happen, right? Unless it's highly curated. Almost never works. I'm going to, real quick, x cubed plus 4x squared. Plugging this into Desmos. Those of you who know Desmos, you probably know exactly what this is. All right, there is one real solution, and it is located at 1.613. That's really close to. All right, 613. And if I just take this and copy paste it into Wolfram Alpha, that'll give me an exact answer. Don't do this in your class, by the way. equals plug in. That was not what I wanted. Okay. One of the problems with Desmos, good thing, but also a problem sometimes, is that they use LaTeX. And so it will occasionally, they're not giving me an exact answer. Okay. Oh, yeah, that's why. Okay. No, we don't want an exact answer. Yeah, that's pretty nasty. They will give me one extra decimal place. All right, if you do it on your graphing calculator, you'll also get out to like 10 decimal places. So we can do that too. Anyway, this was not the point. Sorry. All right, so the point that we were doing was we were trying to figure out what the area between the curves was if we had this here. All right, so excuse me for just 1 second. All right, sorry about that. Yeah, quick question. So not exactly. So my particular institution is a 2-year school, and so I don't carry the title technically, carry the title of professor. The way ours works is you come in as an instructor typically, and then when you earn, you have to have your master's for my institution to teach full-time, and then you come in as an instructor. And then when you do your first 3 probationary years, you do a project at the end of the 3, and it's just like some reflective kind of stuff. You can actually do like a teaching improvement project, which is a lot more involved, but shows your commitment. And that gets you the title of assistant professor, and then you can get associate professor with another 3-ish year project, and then you can get another promotion to full professor after another 3-year promotion project. But it has to be like creating a course from scratch, or like, you know, something really big. Some of our people were like working on higher education commissions, or doing like a lot of other really high level research for like data analytics and stuff like that. Trying to compare our school to other schools and compare us to the nation and all sorts of, I mean, there have been so many different promotion projects, like I don't even know where to start. If like just looking at all of the options that are before me, it's crazy. I have been working on one. It wasn't going, I mean, I was like handing it in as the pandemic started, and then they were like, yeah, you need to edit this a bit, but we're also not doing any promotion projects until the end of this thing. I'm like, so if I had like gotten it in and it was acceptable, I would have been promoted. But it was not really acceptable. It was in kind of a drafty form. Oh well. So I decided to come here and do this. All right, so anyway, we're looking at taking the integral of these functions. So it's the difference, again, between the upper and lower. So the square root of x minus 1. So one of the other things was that I was worried that these were not going to intersect, that the plus 2 here was actually going to cause this thing to come up, and the rational function was going to duck under it. And it turns out that it did actually connect, provided that we actually might want to plug those in just to make sure. So this is going to be 0.61. It's about 0.64, so the estimate is about, root is about 0.8, give or take. Plus 2 should be about 2.8. Okay, so this one should also be pretty close to 2.8. This is going to be like 1/4. Ugh. Nope. Alright, where's my calculator? Oh dear. So maybe it didn't. It has a solution there, but it may not actually be the solution we were looking for. I mean, I should just be doing this on Desmos and graphing it. That's where I have my other information. Square root x minus 1 plus 2. 1 over x plus 3, yeah, plus 1. Yeah, they don't connect. So this illusory or extraneous solution, we actually use the term extraneous. So this extraneous solution actually exists where the functions, so what we actually have here is one that goes like this and then one that goes like this. The extraneous solution will exist, this is at 1, this point is 1, 2. The extraneous solution exists where the negative of this particular function exists. So this is our 1.6135 other stuff by somewhere close to 1 1/4. What was that? 1.214. So, yeah, that's me messing up. But, you know, it happens. Okay. In that case, so this like completely ruined your entire problem. Sorry. But if we want to do one just for fun, we can do one that's much more easily recognizable as actually having an answer. I won't mess around this time, I promise. Okay, so let's do it like this. This is going to be the square root function, and now that function over here. Oops, no, not curly. X is going to go from 0 to... No, hell, why not? 3. In this space. That's not exactly what you wanted either. All right. Can do this one. let's try this. Let's just do this one. F at x is going to be the square root of x. No messing around anymore. G of x is going to be 1 over x plus 1. So this has been shifted back. It's going to drop through just like that. So we want to know for the green one. Let's get rid of this for now. What are we going to do for this? So now we are going to do f, the upper, minus g, the lower. And we're going to go from a, which again we don't know, but we can find this much easier than the previous one. So anyway, square root of x equals 1 over x plus 1. We're going to move this back over the other side, so it's now x plus 1 times the square root of x equals 1. Square both sides. This is now going to be x plus 1 squared times x equals 1. All right, much nicer. This is now going to be x squared plus 2x plus 1 times x equals 1. X cubed plus 2x squared plus x minus 1 equals 0. Shift that to the other side. All right, that's the quick way. If we were to do a positive 1, this would not work very nicely, I don't think. If we do negative 1, this is going to be negative 1, 1, negative 1, 0. All right. Maybe this isn't going to be nice either, but at least it'll give us an answer. Yep, okay. X is going to be about 0.466 is the answer that we actually want to look for. The other, if there are any real, 2x squared plus x minus 1. Nope. Okay. That's all we get. Okay. This is the only real answer. This is the one we're going to work with. Okay. So we're going to take the integral of the square root of x minus 1 over x plus 1 dx, going from our 0.466. Again, keep in mind this is not an exact value. So you do want to have as many decimal places as possible if it's going to be in decimal form. If it's going to be in exact form, then you're going to have an exact form. It's not going to be an issue. And this goes out to 3. All right, so taking the integral for each of these things, this one is going to be square root function is a power function. So we're going to take a power rule from a to 3. I'm just going to use a for now. Of x to the 1/2 dx minus integral from a to 3 of 1 over x plus 1 dx. All right, this one over here is going to end up with, again, we're going to increase the power by 1. So this is going to be x to the 3/2 evaluated at x equals a to 3. But we then have to compensate for the fact that this did not have its power out front of it. So if we were to take the derivative here, the 3/2 would get knocked down, and we should have had the 3/2 here. So my kind of way of doing this is I go back and I say I should have had a 3/2 here to make it a nice clean power function. But I can't just have that, right? You can't just give it a multiplier. So we're going to have to multiply the outside by the reciprocal in order to balance. Right? Now that's Calc 1 stuff, so if you're already in Calc 2 and above, you already know that. But I just personally like to do it as a note-keeping / bookkeeping sort of thing to make sure that my audience understands exactly how I got that number. Right, the other option is you say you divide by the new power. So we divide by 3/2, we get 2/3. Either way, it works. All right, then we subtract. The integral here is, again, this is 1 over x plus 1. X plus 1 or x minus 3 or any of those end up with the same value when you take the integral. So it's just u down at the bottom. This is 1 over u, and du is just going to be the derivative of the bottom, which is going to be dx. So it doesn't change at all. This is going to be the natural log of the absolute value of x plus 1, evaluated when x is equal to a from a to 3. All right, then we take, again, our fundamental theorem of calculus says take the top one, and we're going to plug that in first. So 2/3, 3 to the 3/2, minus 2/3 a to the 3/2, minus parentheses, natural log absolute value of 3 plus 1, minus natural log absolute value a plus 1. Keeping in mind the lowercase a here is just a constant, so we'll get there. Okay, so 3 to the 3/2, we can probably just leave it if you want. We got a 3 down the bottom, so that will divide out one of the 3's, which leaves us with 2 times 3 to the 1/2 minus 2/3 a to the 3/2. All right, minus natural log absolute value. It's a positive number, so it's just 4. This is going to be a plus because we have a minus on the outside multiplied by this minus on the inside. We get the natural log of a plus 1 is going to be 1.466, again, approximate. So get the exact value as close as you can. Sorry, I also did a on this one, so we're going to leave it as a. Stay consistent with your notation. Something I harp on with my students all the time. All right, so 2 times 3 to the 1/2 minus 2/3. This is now going to be that value, 0.466, and again, other stuff raised to the 3/2 power. It's probably not even 466. It could be 4658 or whatever. Just, be careful. Don't round too much. If you round too much, your teacher's going to start getting cranky, because I do. Minus, this is going to be natural log of 4. Remember that 4 is 2 squared, and you can bring the 2 out front. So 2 natural log 2. Plus natural log of 1.466, etc. Okay, so this is the exact value. It's probably not very satisfying. But if you give it a minute here, we'll square root of 3 minus 2/3 times, I only have the rounded version, so yep, this is going to be really ugly, raised to the 1.5 power minus 2 natural log 2 plus the natural log of 1.466. All right, very approximately it is 2 1/4. All right, I got 2.248, but I can't trust that to any more than like 1 or 2 decimal places because I rounded pretty heavily. So if we got a more exact value, i.e. not off of Desmos, if I had actually plugged it into my calculator and got 10 decimal places, then I could probably trust that out to 3 or 4. I don't actually do significant figures. Most mathematicians don't. Mostly what we're doing is you just kind of say, like, here's the exact value, and this is probably what it's going to round to. We're terrible like that. Um, so we'll give you the exact value, and it's up to you to figure out where you want to round it. All right, if you did want the bit that's underneath both curves here, this becomes a little bit interesting. So you do have to say, okay, I want, what's the integral of f of x dx from 0 to a, and then what's the integral of g of x dx from a to 3. So this one's a little bit easier. You'd still have to figure out where a is. I'd mentioned this way back when I was talking about some of the earlier stuff. A bunch of you weren't here, so welcome. When you're looking at like the beginning of a problem, you really want to say, like, how can I break this down, or how can I reword it so that it looks a little bit easier, or it's more like in my language rather than some word problem that you don't necessarily understand. All right. Anybody have any questions? So I do actually have another thing that I was getting to. If anybody has any questions, I am perfectly happy to answer them. But yeah, I do also have another thing if anybody wants to look at that. Just looking for my notes real quick, because again, I might actually have them here. Might have a winner. It's definitely one of my research notebooks. No. Oh well. That's the other one. What kind of stuff about set theory? I don't necessarily have a huge amount of knowledge of like set theory particularly, but yeah, I have done a little bit of work here and there. And I mean, like I was saying before, I did a lot of the history stuff, so like I know the stories with Cantor and all that, but yeah. What particularly might be dependent on what it is that you're asking about. In the meantime, who do we have here? All right, well, Aiden, welcome. So if you all might as well just toss myself out there. So if you all like what you see, this is office hours. Welcome. Um, my name is Obi-Wan Pez, and I am becoming an educational streamer, as well as occasionally doing some, or I'm also planning on doing some gaming stuff on the weekends. I will be here specifically, so N Simplex Pachinko is going to be my streaming platform, and uh, yeah, drop a follow if you're interested. I will be very grateful. This week, I'm calling. So I've broken up my stream into two different groups. Office hours is going to be the math-oriented stream, and after hours is going to be the gaming-oriented stream. Um, branding is great, right? So if you're interested at all, I'm mostly going to be doing I'm mostly going to be doing the after hour stuff on the weekend, either Friday or Saturday. It depends on my schedule. For now, I'm going to try Fridays, and if it becomes too much, then I'll switch to Saturdays or just do a once a week thing. But currently, I am working on Outer Wilds, which is a brilliant, brilliant, brilliant spacey exploration type game. Came out in 2019 from Mobius Digital Studios and Annapurna Interactive Publishing. They are the game is amazingly well. Yeah, hashtag not sponsored. The game is amazingly well put together, and most of the time when I play a game, I'm figuring there's going to be some bugs here and there. Like, this is very tight. It is on Game Pass, so if you already have signed up for Game Pass, you don't need to pay any extra money. So that's wonderful. I played all the way through it, and I bought it immediately. Like, separately from Game Pass, I bought it. And then when I decided to do the stream, I bought it again on Steam so that I could do it on my PC. So, I mean, that's how much I like it. I have only bought like a couple of games on multiple platforms multiple times, and that was one. Anyway, so, ZFC. I'm gonna have to look that one up because I don't remember. Oops. Or it was under a different name when I learned it, or who knows. Axiom of choice? Okay. Zermelo Franco set. Probably not. Oh, yeah. It's been almost 20 years since I've learned that. So, okay, yeah, unfortunately, sorry. If anyone is interested in After Hours and specifically Outer Wilds, I will say I already did my first one. I need to edit it just a little bit, and I'm also going to be reposting all of my videos on YouTube eventually under those two playlists. So, Office Hours and After Hours. My first After Hours is on Twitch still. It'll be there for allegedly 60 days. We'll see. It is, however, a bit of a spoiler. So what I did was I called it a trailhead tour, and so it was just going to like all of the individual first things that you would just happen to stumble on and be like, let's go here, and then read all the notes and do all sorts of stuff like that. So this week, this Friday, I'm planning on doing part 2 of the Trailhead Tour, which is starting to delve a little bit deeper into harder to reach places, and also a little bit into like secondary things that you have to find, like two pieces of information in order to bring them together. So if you haven't played Outer Wilds, I recommend you do try, like I said, either if you have Game Pass, great, do it. If you have time, right? Don't get yourself fired or something, or stay up until 3. Don't do that. Don't be like me. But yeah, if you want to check out my stream, it would be probably better for you in the game sense to like explore all these things yourself and then watch me do it, like for the little parts that you might have missed or something. But apart from that, yes, I will move on. Yeah, Freddy's got that. Yeah, Zermelo Frankel were two mathematicians who came up with these axioms to work together, set theory. So in order to truly be a part of set theory, it needs to match all of these lists of criteria, and need to match all these lists of criteria and make sure that it fits all of the axioms in order to be considered part of set theory. All right, I'm going to back up and go into the other one. It's going to take a while to save, probably. Okay. So I was talking about Fermat's last theorem. Again, this came from Arithmetica. Diophantus was the author. He wrote this. He came up with the Diophantine equations had typically a power, sums of powers. So x to the n plus y to the n equals z to the n, something like that. And Diophantus, who was in ancient Greece, figured out that there were certain classes of equations that could be fit into this mold. And he gets credit for like discovering, or basically anything that's created that's similar to this is considered yeah, I'm not solving it or anything. Anything that's like of this form, and like anything even randomly similar. So this is like also 1 over x to the n plus 1 over y to the n plus 1 over z to the n is also considered Diophantine equation. So look up Diophantine equations if you're interested. It gets into a whole lot of other stuff. I'm just like glossing over a little bit of work that I did, and this did not in any way come to any sort of fruition. But I thought I would share it because I just found it interesting. It was a neat little problem that I was working on. So like I said, Pierre de Fermat came up with this particular equation, or pulled on the thread of this particular equation, and said that he had a proof that no integer solutions existed for n is greater than 2, where x, y, and z are integers that are non-zero. And it took until Andrew Wiles in 1993 to 1995 to come up with an actual proof to say that yes, there are no integer solutions. And his proof is like 100 pages. So there was pretty much no way that Fermat came up with that. I had mentioned this a while back in the stream, but again, we had some nice turnover, so yeah, it's a ridiculously long proof. So the Beal conjecture was discovered by, or first asked about by Andrew Beal, or Andy Beal, he goes by Andy, which says that given x, y, z, a, b, c are all positive integers, and x, y, and z are greater than 2, then this equation has this equation says that, if this equation is true, a to the x plus b to the y equals c to the z, it's a generalization of Fermat's last theorem, then ABC must have a common factor. This was first proposed in the 80s, back when computers were first coming out, and Andy Beal worked in some software development company somewhere, and this kind of popped up at some point as like a way to test computers. And so we want to see whose computer is fast. So one way to do it was find digits of pi, right? And that's the way we do it now, pretty much, is who can figure out the most digits of pi as far as we can go. A quantum computer, I'm hoping someday soon, will come up with a record number of digits of pi in a record time. So right now we keep having it keeps going further and further, but it takes longer and longer to get there with classical computers. At any rate, when Andy Beal was in charge of this development company, he came up with this extension of Fermat's last theorem to test if his computers could come up with any solutions. And this particular one just kept going, and he couldn't find any. And he said, okay, interesting. The only time that we actually get solutions to a to the x plus b to the y equals c to the z is when a, b, c have common factors. So he put it out there with like a $10,000 prize or something like that, and said if anybody can figure it out, it's going to be $10,000 to you. Publish it in a journal somewhere, and the first person to publish it and get it refereed and all that stuff will get $10,000. Now keep in mind, this is 1984, 85, 88, I don't know, somewhere in there. So that's kind of a lot of money. And at some point he raised it in the 90s, I think, and then around 2010 he raised it to $1 million. So it is worth $1 million if you can prove the Beal conjecture. And I was like, why not just take a look at it? I'm not going to do it, but why not just try it out for a weekend or something like that? I had nothing better to do. I was at my father-in-law's place and sure, let's do it. Yeah, so it wasn't like it wasn't like a huge amount of money, but $10,000 could at least get you a good down payment. So nowadays, so I looked at other people's work on Beal conjecture. There wasn't really anything that I could find. I think most people have just kind of said, you need some really high, you need some high level math in order to do this, and I'm not going to get it, so whatever. So I just said, okay, let's look at this a bit. And now it's still not proven. And I kicked this around for a little bit and said, just looking at this, we start here, and then we have to go here to find a common factor. And I said, that's not really working for me. So one of the things that I did was I pulled upon my logic class. And I said that if you're trying to prove a statement that is A implies B, then it is logically equivalent that you could do not B implies not A. So this is called the contrapositive. So I decided to go the opposite direction, and I said, let's negate everything that's in here and reverse the if-then statement. So, given that all of this stuff is still true, that x, y, z, a, b, c are all positive integers, x, y, z are greater than 2, if a, b, c do not have a common factor, then the equation a to the x plus b to the y equals c to the z has no solution. Now you might look at this and say, well, that's just as hard. Why did you do that? And in some ways, yes, it is just as hard to go that way. However, I decided, well, A, B, C do not have a common factor. Okay. So this means, check my notes real quick, that A divided by some D, B divided by that same D, C divided by that same D, are not all integers. All right, so this is my starting point. I'm saying that, yep, okay, either any one of them could break this, or any one of them could be true, that they have a common factor, or any one pair could have a common factor, or none of them can have any common factor at all. So I had to prove a couple of different things. So I said, all right, D does not divide A, or D does not divide B, or D does not divide C. Could make this work. Sorry. Or some combination of D does divide A, well, I guess if we're doing right, if we're doing or, then this could be split into multiple cases itself. So this could be sorry. I split this into multiple cases. Here we go. This is awful because I don't actually have the notes that are done. I have notes that are like half-assed. And it's just awful. So this is going to split into a couple of different things. We got D does not divide A, but D does divide B, and D does divide C. Now this is going to be equivalent to D dividing A, D not dividing B, and D dividing C. Right, it is going to be equivalent. So this reduces the number of cases you have to check. The only one that you have to potentially worry about is D divides A and B, but not C. Of course, then what I do is I just kind of reverse it and then just say it's the same as the other one. So this is pretty much the same. Now this case was super easy to prove, and you all could probably do it in 5 minutes. If D divides two of these numbers, then what we've got is I'm going to manually decide to let W be the least common multiple. Nope. Nope, that's wrong. All right, let W equal the minimum of exponents x, y, z. So then what I do is I say, okay, let's take our original equation, a to the x plus b to the y equals c to the z, and we're going to multiply it by 1 over d to the w. So whatever the minimum exponent is across the board, That's what we're dividing by, d raised to that minimum exponent. So now this is going to get us an a to the x over d to the w plus b to the y over d to the w plus, nope, equals c to the z over d to the w. All right, well now we can factor some of these out. So I'm going to factor out w d's with w a's. So this is going to be a to the w over d to the w times a to the, what's left is x minus w. If x was the minimum, now it's going to be a to the 0 as the leftover term. Okay, plus we're going to do the same thing over here. This is b to the y divided by d to the w times b to the, nope, man, sorry, b to the w over d to the w times b to the y minus w equals, how close? We're pretty close. All right, c to the w over d to the w times c to the z minus w. Oh, so close. No, I don't think we're going to do it. Okay. There we go. I think you all know what I mean anyway. Then, depending on what case we had, we've got now a over d raised to the w times x, a to the x minus w plus parentheses b over d to the w times b to the y minus w equals c over d to the w times c to the z minus w. All right, and then in all these cases, what happened was a over d, b over d, and c over d are potentially going to be either d divides them or d doesn't divide them. In the case where we have one that is not divisible, only one, then what happens here? Well, let's say that a and b are both divisible by d. Then we have a over d is an integer, and b over d is an integer, and raising an integer to a power is an integer, and multiplying by an integer to a power is an integer. So these two things on the left, if a and b are both integers, the whole thing that we do there is integers. This is all what we call closed under integers. Or the integers are closed under those operations. So everything we've done here, provided that d divided a and b, we're good. The left-hand side is an integer. The right-hand side, on the other hand, c over d, we already said for this one here, right, c over d is not an integer. So how can you get an integer to be equal to a non-integer? Doesn't work. Right? And raising a non-integer to a power isn't going to get you an integer either. So, doesn't happen. So in this case, we can now prove that this does not have a solution. So we get a big check mark here for this last one. If we said that d divides a and b and c, now we've violated the first part, right? The whole predicate at the beginning here. We said if a, b, and c do not have a common factor. So d cannot divide all three. So if we divide any one of them, we can always group the integers together and then have one non-integer term on the other side. So that is my contribution to this. The problem then arises, well, if we want to now do 2, so any 2 of them are not divisible, then D does not divide A, and D does not divide B, and oops, D divides C. Or if we do the other one, D does not divide A, and D does not divide B, and D does not divide C. Right? These are the only 2 cases that really matter at this point once you've gotten past this. Right? Again, all 3 of these cases are pretty much identical. So we can just say any one of them is not divisible, and then we group the divisible terms and the non-divisible terms. Down here, when you get the 2 or more non-divisible terms, now we're kind of stuck, because I can't prove that 2 non-integers, when added together, won't get me an integer. It's still going to be possible. You get what, like, 1/4 and 3/4, right? You add them together, you get 1. So there are some interesting threads to pull on from this point. There may be higher mathematics that I just don't know, or I haven't recognized it, or even something that's super easy and I just haven't recognized it, that I could do from here and show that it's just not possible to get a solution. But at this point, I don't know. So that's my presentation on, on the Beal conjecture. If anybody does, take this and run with it, go for it. It is, like I said, just kind of fun to play with. And why, thank you. It is just fun to play with. I did say, a lot of times mathematics just comes down to, like, did I have fun with something or not? Do I want to just pull on some threads? Am I interested in something? Nah. This is number theory, but it's really not difficult number theory. This is just common sense stuff. So, like I said, making sure that when you have something over here, when you have an integer, you raise it to a power, it's still going to be an integer. When you multiply an integer by another integer, it's still an integer. When you divide 2 numbers and the bottom number divides into the top one, clearly, by definition, it has to be an integer. So yeah, this is the sort of, like, recreational math that would be really interesting to get into and play with. Some other people have done, like, prove the Pythagorean theorem in a different way. And, I mean, this one pretty much is the Pythagorean theorem, but that was one of the other things, was President Andrew Garfield was actually also, just like Andy Beal and Pierre de Fermat, was also a recreational mathematician. And Andrew Garfield also created a brand new, at the time, proof for the Pythagorean theorem. I think probably you've seen that one before. It was entirely geometric. Ew. Alright, whatever. Let's see, how did it go? Is that? No, that's not right. No, that was it. Okay. Oops. Pretend that's a square. if you can. Yeah, no, that's going to be terrible. Okay, whatever. Anyway, so Garfield's proof basically said, okay, treat these small sides on the right triangles, because these are all going to be right triangles. Treat them all as A. And then the big sides are all going to be B. And then the big sides on the outside are all going to be C. Lana! How you doing? So Garfield said, or yeah, James Garfield. Okay. I keep mixing up Grover Cleveland and James Garfield in my head. Anyway, so Garfield said if we rearrange all this stuff, what you can do is actually rearrange these tiles inside of this square so that you end up with one, what is it? One A, B, right triangle this way, this one this way, and then one big, was it? It's online. Everybody can find it. This is embarrassing if I get it wrong, but it's okay. All right, so they are identical rectangles. These are totally identical, and if anybody else tells you otherwise. And then, yeah, these are horribly wrong. All right, hang on. I wish I could copy this and just like break it apart. You can actually do this in Paint. If you take all these pieces and break them apart, you end up getting, like I was trying to do. Okay, here's one. Big one here, I think. Not that long. I mean, like I have a grid here, I just can't see it. There. Nope. That's got to be wrong too. All right. Let's look it up. All right. In one image. Come on. Oh no, I'm completely wrong. Cool. Yeah, I was doing the complete wrong thing. This is somebody else's. This is a really good one. But yeah, Garfield's proof was if you had ABC like this, and then you do lay B this way. That's totally the same. So yeah. Draw a triangle that way. You got C here, you got B here, you got A there. And now this is a right triangle, this is a right triangle, and this is a right triangle. Here you've got a rectangle. Nope. You've got a distance going across here. That's A plus B. Here you've got A, and here you've got B as areas. Yep, okay. as area of the trapezoid. We could also create this as area of the trapezoid. So here you say that in order to get the trapezoid, it is the average of the sum of the bases, so 1/2 a plus b, times the height, which is also a plus b. And also, if you rearrange sorry, got a 4-year-old, sometimes wakes up. No, okay, it's the lo-fi. Go figure. Right, and the area of this other stuff, if you broke it up a different way, the area of the right triangle here is going to be 1/2 c times c. And then the area of the individual triangles is 1/2 a times b, but there are 2 of them, so you get a plus b, or a times b. So over here you expand this whole thing, 1/2 a squared plus 1/2 twice ab is just going to be ab, plus 1/2 b squared equals 1/2 c squared plus ab. And guess what? Take out the ab terms here and here, subtract them, and then multiply everything by 2. And now you've got a squared plus b squared equals c squared. I gotta figure out who did the other one, though. What do you call that? Box proof? Yeah, that's the one. That was it. Okay. Yeah, I was off by a bit. No surprise here. All right. Yeah. Oh yeah, way off. I don't want to get too overzealous here. I'm skipping frames occasionally. Okay, that's enough. Yeah, so that's Pythagorean theorem proved in different ways. So again, this other one down here was the James A. Garfield proof. The President of the United States back in the 1800s. Like, not the, but you know what I mean. The James A. Garfield who was president. But the other one that we wanted. The other one that I was trying to do, right? You make a big square like this, and then the of course, now I'm going to draw this wrong, but whatever. This is better. It's closer, so it's not 100%, but it's at least you get the point. All right, so label the small ones A, big ones B, and then the triangles here have a hypotenuse C. This one's all visual, and I like this one a lot, mostly because it's all visual. You don't need to prove anything necessarily. So here you've got a c squared in the middle, and all around the edges, again, this is like the a times b thing that you've got on the other one. Yeah. So we've got 4 1/2 a times b's. So those are the triangles that we have, plus a c squared. If you rearrange it instead, and you take those 4 triangles and put them, so we keep this one here. We keep this one here, but now we take the other one from the other side and we push it through the center till it gets to there. Then it ends up finishing a rectangle. Here we have A, here we have B. Then you do the same thing on the other side. You take this triangle. Yeah, that's fine. So you take this triangle and you bring them together, and I'm going to shove them off to the other side over here. So it makes one that goes this way, and this is where the totally not to scale comes in to play here. So this is also A and A, totally. And this is also B, and this is also B. Again, really it's just a matter of shifting stuff. I'm terrible at drawing. My students will attest. So again, we've still got 4 1/2 ABs, but this time we've got here a B squared and here an A squared. And we can set them equal to each other. Night, Freddy. Sorry if I missed you. Yeah, so I really like these like low-tech proofs of the Pythagorean theorem. Like there's a way to do it with the there's a way to do it with like using only Euclid constructions and stuff like that with a compass and a straight edge, and I did that once and it took me like an hour just to copy it from somebody else who did it, and I was like, this is not fun. It was interesting to see it. It was important to work through it and say like, yes, I can prove it definitely that it absolutely works. I will never do it again. And you know, if I have to tell an Algebra 1 student that, or a geometry student, that this is how it works, I will definitely use one of these methods 100% before I ever do any of that like Euclidean construct. No. It's just unnecessary. All right, what do y'all think? I think if anybody has any questions, you can let me know in the chat, and we'll see if we can do something for you. But other than that, I think that'll do it for me. If you want, my same tag is an email address at gmail.com, and you can send, like if you have questions and like with a picture or something like that. I will say that if it is something in a published book, I probably won't be able to actually use it. So, I mean, Soul Reaver, I kind of did that one almost exactly the same, but yeah. I'll be able to... Professor Pachinko, there we go. So yeah, if anybody wants to drop any questions in there, I'll be there. Yeah, we don't want to mess with copyright. Of course, my name is fraught with disaster, so that's one of the reasons why I created this channel under this name. And I will only say my personal name out loud. I will not ever put it into print. Alright, so with that, I think I'm going to stop the stream for tonight. Oh no, I did not record any of this. Alright, I'll record it later. I guess probably tomorrow or something. I'll just put it on in the background and hit record. Oh well. Well, it's on Twitch at least, so... Yeah, like I said, I'll probably just record it from Twitch and then put it on YouTube. All right, cool. Anyway, have a good night, everybody. My name is Obi-Wan Pez. This is N Simplex Pachinko on Twitch, and I will see you all hopefully either on Friday for Outer Wilds or on next Wednesday for more mathy type stuff. Have a good night. Salchi Papas. All right. Oh, I can raid somebody. Wait. I have that power now. Oh no, I don't rate it. I don't have anybody. Of course, the other problem is I don't know who's online, so. All right. If everyone doesn't want to, if anyone wants to stick around, I will raid somebody. But if not, have a good night, and I will see you later. Oh, man. I think I'm going to raid Jason Charles Miller because he is an awesome musician. So, yeah, if anyone wants to stick around for that, I will do so in just about a minute. Yep, there we go. All right. So here we go. Gonna head on over to Jason Charles Miller. Have a good week, everybody. See you later. Thank you so much for coming. Can't tell you how happy this made me.